Well, hello everybody, and welcome to MacDermid Enthone's discussion on ammonium and boric acid free acid zinc electroplating process. My name is Robert Collin. I'm the America's Technical Manager for MacDermid Enthone, and I'll be the moderator for this event. The presenter today will be Mike McCoy. He is our anti-corrosion business development and product manager. For any and all questions you have, please submit them in the questions and/or chat room within this webinar. At the end of the session, we will do our best to answer them all. If we cannot get to some of them, we will contact you directly via email. Thank you again for taking the time today to learn about MacDermid Enthone's ammonium and boric acid free acid zinc. Mike, the presentation is all yours.
Thank you, Rob. Good morning, everybody. I am the Business Development and Product Line Manager for anti-corrosion products in the Americas. I have approximately 25 years in the anti-corrosion market space. And today we will be talking about KenLevel BF2, which has some very, very unique qualities and advantages in production, throughput, and also sustainability. A little bit about this presentation is that this process was originally developed for the brake caliper market. So there are going to be pictures on brakes and there are going to be descriptions about brakes. And I want to preface this by saying this process has been very beneficial in barrel plating as well. And I will explain some of that as we go along. So we have had some successes in the brake market, but we have really been successful in moving the needle as far as sustainability and environmental advantages. So first off, one of the main advantages to being boric acid and ammonium chloride free is that the buffering system that we use allows you to plate at very high current densities. You can see here that 6 to 8 amps per square decimeter, approximately 60 to 80 amps per square foot. That is attainable. That is a number that we have performed in our testing, in our beta site testing, and in our pilot lab processing parts. So what this means in a barrel application is that you can increase your barrel loading and handle higher current densities with no perf marks. You know, we can run approximately 40 to 50% capacity in a barrel. We are able to have high air agitation, and it is a low foaming process. So because it's boric acid free and ammonia free, that also allows for easier waste treatment, no boric acid crystallization. It's a liquid additive, so we don't have the difficulties of dissolving boric acid into the electrolyte. And again, that also allows us to have automatic replenishment. So this is a quick content slide about what we're going to cover. So as I described, ammonia and boric acid are used to control the pH. It is used to control burning. Okay, so with the additive that we have, which is simply called KenLevel BF2 Buffer, it removes the ammonia. It removes the ammonium out of the waste treatment system. And we all know how difficult that can be as far as complexing metals. But one thing that we've discovered and has been very advantageous is that there, depending on the municipalities, applicators can get surcharges for ammonia in their waste stream. And we've been able to provide extreme benefits to wastewater treatment by eliminating ammonia from the stream without complexing metals and without incurring surcharges. Boric acid is now on the SVHC list. It has not been given a sunset date yet, but solutions that are 5.5% by weight are classified as a substance of very high concern. So as mentioned, this is for rack and barrel, low foaming. It's the other benefit to this process is that it has very good throwing power, which is one of the reasons why it's very good for brake calipers. It's a very bright deposit. there are two separate brighteners that can be used depending on your operating temperature, but the bath itself is going to provide a lot of brightness and grain refinement without having to add a lot of brightener. So that means you're going to have less chances to have brittle deposits and chipping. So these are some of the regulations, the global regulations that are in place now. You know, we all know the REACH and ELV limits. You know, now we have the global harmonized system of classifications for labeling that's been in place, you know, the SDSs and whatnot. So the environment of our industry is changing all the time. If you think about way back when we were doing cyanide cadmium plating, you know, it's all beneficials and hexavalent chromates. So as all of these regulations have come into place, what it's done to our industry has forced us, and to a benefit, improve our processes to be more sustainable, to be more globally friendly towards the environment. And in that, we've also increased our process capabilities as far as throughput, as well as corrosion resistance requirements. Specifications are rising because a lot of these environmental concerns, and we have answered the challenge by developing new processes such as KenLevel BF2. This is the actual list from the European Chemical Agency, where you can see that boric acid is on the list, as well as other borates compounds. And this is the Annex 14, and boric acid is on there as a substance of very high concern, toxic for reproduction, which is a main problem for these various substances. So they're always updating these lists. Boric acid just happens to be on one of them now, and we are in the process of addressing these substances as they arise. So a little bit about the process itself. And, you know, mentioning again the boric acid free, the higher current density is extremely important and extremely beneficial, predominantly for brake caliper applications, because of the high current, the high surface area of the parts themselves, plus the complex geometries. So if you want to plate parts with complex geometries, this is a very good process to cover your low current density areas without burning your high current density areas. We operate at a lower zinc metal concentration, and that also helps with throwing power as well. And obviously, it's going to reduce your waste treatment concerns and your cost of buying metal anodes. So what we are looking at here is just a graph of current density versus pH. And you can see that without using any buffer at all, you know, you're going to rise in pH fairly quickly. The other two lines are buffer, the BF2 buffer, and with boric acid, and you can see that they have a similar effect in controlling the current density, or excuse me, in controlling the pH value. This is a slide that shows the crystal structure, the grain structure of a boric acid bath and a boric acid free bath. And you can see that the numbers are relatively the same as far as 101 and 100. So we're providing a similar crystal structure without using boric acid. So here we have a whole cells on the left with a new makeup, and on the right with boric acid, 1.5 amps, 15 minutes. You can see that it is a burn-free deposit. After aging at 20 amp hours per liter, you can see that we still have the same anti-burn characteristics. There's actually an improvement in the BF2 versus a boric acid. You can see a little bit of a haze or of the beginnings of a burn on the boric acid containing material. And that is, it mentions here that this process can be controlled by hull cell analysis. We do have an analysis standard for zinc and chloride. We can analyze for the buffer component as well. And it is easily maintained by daily hull cell analysis and routine chemical analysis. One of the things that is a problem for acid zinc plating, whether it's boric acid, ammonium chloride, or in this case, boric acid free, is your distribution. We all know that the extreme high efficiency of acid zinc can lead to very thick deposits in high current density areas and very thin deposits in low current density areas. You'll notice here that on these breaks, we're taking 3 or 4 different spots, and we have fairly uniform deposits. You look at 1, 2, 3, and 4 on the upper left, and we're going between 12 and 20 microns or so, which isn't too bad for a brake caliper distribution ratio. We've seen highs here of 20 and lows of 12. So that's a pretty good representation of the uniform thickness that this process is able to achieve. So one of the things that is concerning, this is particularly towards rack plating and also brake calipers, but one of the extreme challenges to brake calipers is the plating initiation. So you have to cover up all your porosity, and then you just start building thickness. And you notice that at 2 minutes, we are covering in the high, and we still haven't started to cover in the low current density areas. At 4 minutes, we can still see a little bit of lack of coverage, but at 6 minutes only, we are fully covered inside that claw area, so to speak. And now we're just building thickness to the required specifications. So the initiation speed, which in this application is extremely important, this bath is very, very efficient at starting the initiation right away without burning the high current density. These are a couple pictures from our alpha site, and you can see that we are running high air agitation, and we are not over foaming the tank. There is some foam on there, but it's not egregious at all. And these were done at the higher current density as well too. So we were talking about the benefits of the higher current density without burning, and that can go and rack plating towards rack loading. So we're able to rack more parts. We're able to increase production by using this process that is related to the higher current density, the higher rack loading, and in barrel applications, it's related to higher barrel loading. More weight in the barrel, more parts in the barrel, more throughput, approximately 20-25% more throughput per hour or per shift with this process because of the advantages of the higher current density and barrel loading. So we do have a wide operating window. It might be a little bit difficult to see what those exact numbers are, but what you can look at is 25 degrees C, 77 F, and 30 degrees C, 85 degrees F, depending on the brightness level and depending on the desired brightness level, and also your operating temperature will determine which process is the best benefit for your application. You can see we have 35 degrees C here, which is about 105 degrees. So we are able to run this bath warm and obtain the same amount of brightness without evaporation of the brightener itself. So as I mentioned, there's 2 brighteners. They are used independently depending on your operating temperature. KenLevel BF2 Brightener can be used. It says 20 to 40 degrees centigrade. That's 68 to 110 or so, 115 Fahrenheit. And we use a low temperature brightener, which is the BF2 LT, if the bath is able to be maintained under 85 degrees. Now, we do have some applications that are running the LT brightener at elevated temperatures, and they're not running with any difficulties at all. They're still running very good work, very bright work at a lower consumption rate. Again, burn-free deposits and throwing power in the brake industry, depending on the application and the part itself, we are able to throw all the way into that bore area. This is KenLevel BF2 PrimerPass 3098 HC is a thick film, high corrosion resistant, mild iridescent passivate. And you can see we have 240 hours, no white corrosion, 500 hours, no red corrosion. It's a very good process for the receptivity of passivates. Sometimes AcidZank deposits have been known to not be very receptive towards passivates or chromates back in the day. But this process does allow for acceptable passivate layers. So brightness and color are really going to be a benefit, as well as leading to the corrosion resistance. So our operating conditions. We had mentioned the temperature range. Obviously, if we can keep it on the lower side of the range, it's not always possible depending on the equipment installed. We have the opportunity to choose the brighteners, as I had just mentioned. pH, standard pHs for normal acid zinc plating, we run it a little bit on the lower side, sometimes depending on the application. Current densities, you can see here, 20 amps per square foot, but we can go as high as 80. And in a barrel, we're looking at about up to 10 amps per square foot, which is really good for a barrel if you're able to draw that current. Excuse me. Somewhat standard applications for rack and barrel. 30 grams per liter on a rack. It's about 4 ounces per gallon. Chloride levels. The chloride is in range with other types of systems. Carrier comes in at about 3.5%. So if before you were running a boric acid system at, say, 5 ounces per gallon, this is going to be running at about 3.5% to 6% maximum. The brightener we talked about, you can see that it's at a low concentration. The standard brightener is at 0.5 ml per liter, which is not a lot. That's not a significant amount of brightener that is needed for the deposit and to produce the proper grain refinement. The buffer that replaces the boric acid is 5% by volume. And yes, we are able to convert baths. So doing conversions, we usually ask applicators to stop adding either ammonium chloride or boric acid until they can get that number down, because we're obviously just dealing with drag out. So we wouldn't fully convert a bath until we can get up to that 5% of buffer. And we still analyze for boric or ammonium because we want to see that number coming down. So that's an important factor to know, that you can convert and run these systems simultaneously while you're going through the conversion. It's just going to take some time depending on your application. Barrel parameters are somewhat similar as well. So we one thing that we always recommend, obviously, is proper pretreatment. And the pretreatment will also go to initiation. If you're running hardened fasteners, you have to have proper pretreatment. If you're running brake calipers, you have to have proper pretreatment. Anything with complex geometries. So this is pretty much a standard pretreatment cycle. With cleaning and pickling, and the brakes, we do use ultrasonics, and then BF2 passivation, and then a sealant is usually applied as well. So the additives that we had spoke about, the carrier, does provide grain refinements across the whole current density. It's the wetting agent. It solubilizes the brightener. It's only used at about 1 to 2 liters per 10,000 amp hours, which is not a significant requirement. It is consumed by drag out too. So depending on part geometry and depending on line speed and everything else that goes to drag out, barrel perforation marks, holes versus slots, and that type of information, that will all affect the carrier consumption because it is consumed by drag out. The brightener, the standard brightener, it does provide the grain refinement. It does provide the brightness. It shouldn't be overdosed because of the brittle deposit, but because the process is naturally bright, it doesn't need a lot of brightener. So we're looking at 1.5 to 2 liters per 10,000 amp hours. So now we're talking about 4 liters per 10,000 amp hours. So we're talking about a gallon of product, a gallon of material that's going back into the system every 10,000 amp hours, and we feel that is a very achievable number, and we've seen that in the field as well. The LT brightener is the low temperature brightener. We've mentioned this, and that consumption is can be a little bit on the higher side. You can see the upper end of that is 3 liters per 10,000 amp hours. So, but again, that would be used at lower temperatures. So the BF2 Buffer, which is the boric acid replacement, controls the pH, controls the burning. It takes the thickness off the high and puts it in the low. It does exactly the same function as ammonium chloride and boric acid. What's beneficial about this system and using this buffer compared to ammonium chloride is that ammonium chloride is a really good anode corroder. I mean, it attacks those anodes. It also attacks your equipment. It attacks your steel superstructures. It's very good at being aggressive, I guess, is the way I'm putting it. So by using this system without using ammonium chloride, that means you're going to have better control over your zinc metal concentration. We all know that ammonium chloride is going to corrode the anodes, and the anodes are going to dissolve, and the metal is going to go up, 5 to 6 ounces per gallon. I've seen baths higher than that. Because we don't have ammonium chloride in it, that means we're not going to be dissolving the anode during idle periods, during the weekends, during shutdowns. You're not going to have to be worrying about metal rising over a long period, as we probably are experiencing right now. I'm assuming that if customers are shut down right now and they don't have a holding tank to hold 10,000 gallons of solution, when they go to flip the switch on when this pandemic is over, which we all hope is sooner rather than later, their zinc chloride or their zinc metal in the bath could be extremely high because of the ammonium chloride level. With the BF2 buffer, we don't have that type of problem. We don't adversely raise the metal by corroding the anodes when we don't need to. And you can see that the consumption, again, about 0.5 liter to 1.5 liters per 10,000 amp hours. So some customer experiences. Standard pretreatment again, electroclean, pickling. This happens to be an ultrasonic rinse in this case. AcidZank. You can see we're running 65 to 75 amps per square foot in this particular example. The PrimerPass Ultra 3 is a thin film, cobalt-free blue bright deposit. And the PrimerPass 3098 HC, as you saw in the past slides, is a thick film, mild iridescent passivation. You can see this is a very standard cycle. It fits very well into standard plating lines. So on the left is the Ultra 3. On the right is the 3098 HC, which the operating conditions of that passivate itself can be manipulated to produce an iridescent or a blue bright appearance. So one of the reasons why we developed this process was for a brake company called Akebono, and it came out of Southeast Asia. So we started working on this process for them because, you know, we always do our market analysis and our research about what the market demands. And one of our larger customers happened to come in and say that, you know, this SVHC problem with boric acid is coming. We don't want to go to a ammonium bath. What can you do to help us? So that's one of the reasons why we started to develop this process. And in this application, 72 hours was the requirement with no white, and 192 was the requirement for no red. So again, ammonium free, previous process, no. KenLevel BF2, yes. And obviously we've talked about the benefits, right? Waste treatment is huge, huge. We have customers that are being fined surcharges, thousands and $10,000 a month, a year, depending on the applicator, or depending on the size of the applicator. That goes right to the bottom line. That's money that is not going out of the company because you're doing things differently using this process. And I think that's a huge advantage. The other advantage I just mentioned too is, as mentioned here, less corrosion on your plant and equipment. You know, I know that in Asia, the preferred process is a full ammoniated bath. So we're talking 200 grams per liter of just ammonium chloride, and it's chewing up every superstructure around. Everything's rusted, everything's corroded. You don't have this problem with this system. Again, boric acid free, future legislation, and the no precipitation on the anodes. You know, your anode bags aren't going to, and your anode baskets aren't going to get not solubilized, but aren't going to be coated with boric acid if the concentration is too high, and you lose solubility. You don't have that problem with this process. Air agitation, another one. You know, we can run at higher levels of air agitation, so we don't need to focus so much on eductors. We do still use and recommend. You know, filtration is important, but the solution movement provided by eductors is very, very aggressive, and we can handle the anti-burn and the issue with this process rather than running eductors. We can run at a higher level of air agitation because it's low foaming. We mentioned about the zinc metal, and we've also seen some pretty beneficial results. You know, 50 degrees C is 150, 155 F, something like that, and we are able to obtain those types of high cloud point because of the particular carrier system that we are using. So you know, we don't have to worry. You are going to see some benefits as far as without having to purify the solution, you know, less carbon and permanganate treatments, and it also allows you to run at a higher operating temperature. So the higher operating temperature is going to go to throughput. It's going to go to anti-burn if you're on a rack, and it's going to go to higher barrel loading on a barrel application. So I've mentioned conversions a little bit before, and this is a pretty good thing. You know, it says here on the bottom, small scale lab investigations using hull cell. That's what we normally do to do a conversion. You know, we take 100% bath that as it is now, and 100% BF2 bath, and we do different wholesales and different mixing, 25% to 50% to 75% to go along with the conversion, because conversions are needed. Without the ability to do conversions, you know, making up a whole brand new bath is certainly more costly. So it's real simple. You have the old process and you have the powdered boric acid. Stop adding those. We've done a few conversions, you know, here in the States. I want to say we're probably up to half a dozen at least on this new process, rack and barrel applications. And it is as simple as stopping the old process and starting to add the BF2 process, predominantly the buffer. So as you drag out boric acid and as you drag out ammonium chloride, we replenish the buffer, and it is analyzable. So with that, thank you very much for spending some time with MacDermid Enthone today.